Pinaki, for giving me an opportunity to present my work. I will be talking about the atomistic simulations of plasticity and fracture, particularly in BCC metallic nanowires. Can switch off the slides? So, this is the outline of my talk. First, I will just introduce what is metallic nanowires and then little bit of plasticity and fracture, and then the deformation of fracture of nanowires. What are the difficulties arising out of experiments which leads to look for an alternative like simulations which has an advantage in many aspects over the experiments. And then I will talk about our work on the deformation and fracture of BCC nanowires which iron as a model system. Okay. Then how I will also introduce how to carry out the whatever the load tensile compressive in the simulation methodology, and how to analyze the results to get meaningful results in terms of dislocation, in terms of twinning and other grain boundary defects, and then what are the influence of various parameters like crystallographic orientation, loading direction, tension, compression, and then the system size or nanowire size, then the temperature and the different grain boundaries, and also some work on copper and a separate work on a dislocation behavior. As we all know that the nanowires are something wires which have a diameters in the range of 10 to the power of minus 9 meters, and H has an aspect length is much larger than the diameter. The diameters range from single atom thick to a few hundreds of nanometers, and which have a aspect ratio larger than the 1000. Since nanowires have a very high surface area to volume ratio, and also the other important factor in this deformation is that they have a very limited defect density. It means sometimes there is no defect at all, and because of these things they have a higher superior electrical, optical, other mechanical properties. So, they have a fine application in NEMS and MEMS and other miniature devices. So, we all know that there are mainly in any materials, particularly the crystalline materials, there are two types of deformations, that is by dislocation slip, and the other one is a twinning mechanism. Dislocation slip is basically a shear between two sections of a crystal. As you can see here, this is a perfect crystal. If you apply some load, it will undergo a slip, which basically is a shear between the two crystallographic planes. This slip is not actually a spontaneous, but it is a systematic movement of a line defect. It just like does not occur a spontaneous manner, but it is occurs by a systematic movement of dislocations, and there are various dislocations which we call based on character. They can be classified into edge, screw and the mixed, and based on their Berger vector they can be called as full or partials, and based on their mobility, based on their movement, we call them mobile or immobile. This slip or the dislocation movement does not just like occur in any plane, any random plane in a crystal, but it is restricted to a particular slip system that we call as slip systems. They occur in for example, you take it that depends on the basically a crystal structure. As you can see in FCC, they occur in slip occurs in a 111 plane, a family of 111 planes in the direction of 110. So, these two are basically a closed pack plane, and this is a closed pack direction. So, there are 12 such kind of systems in a unit cell of a 1 FCC, and similarly in BCC there are 3 different planes, all have a same slip directions, and total there are 48 slip systems in BCC. Now, apart from slip, there is other interesting mechanisms, that is the twinning mechanisms, where you can see the deformed part. Let us say this is a deformed part is related to the parent one by the mirror symmetry. Means the deformed crystal is just a mirror reflection of the parent undeformed part. So, it also occurs, the twinning occurs like a slip occurs by a systematic movement of dislocations. Twinning also occurs by a systematic movement of twin boundaries. As you can see, twin boundary is just interface between the undeformed and deformed part. So, it occurs by a systematic movement of these plane defects, and this also does not occur in random plane, but there are some restricted planes systems. You can see that FCC it occurs in this plane, and BCC it occurs in this plane in this direction. So, we all know that mainly in bulk materials the deformation occurs by a slip mechanism, but certainly in extreme conditions like low temperature and high strain rate, the twinning also occurs. even though it is rarely reported, but if we go to very low temperatures and extremely high strain rates, twinning has been reported. And we all know that the dislocations multiply in bulk crystals by a well known multiplication mechanism, that is a Frank-Reed source mechanism. I think all of you are aware that this Frank-Reed mechanism is a main mechanism responsible for the multiplication of dislocations in a bulk crystal. Now, in these crystals, bulk crystals, the deformation and fractures depends on many parameters like temperature, strain rate, grain size, etc. And we all know about good things about these things. But how does the fracture, deformation and fractures proceeds in metallic nanovoids? In other hand, in other way, how the deformation and fracture changes when you have a very small size of the samples. So, there are because of small size, there are difficulties in experiments like sample fabrication, like yesterday what Nagamani has told. There are difficulties in fabrications with controlled size and geometry. There are also difficulties in applying load and getting the stress and strain measurements and characterizing using various microscopic techniques, and it also comes with an expensive. So, we used an alternative technique, that is a computational technique we call molecular dynamics. It is basically in this molecular dynamics we assume that the system is building block of atoms, and the atoms are interacting via interatomic potentials. And in these simulations, no explicit electrons are involved, but their contribution is included in the interatomic potentials. Okay. And once you know the individual atoms and once you know the potential, you can get the trajectory of the particle by solving the simple Newton's equations of motion for a system of particles, a many body problem basically. So, once we have a time, this is basically can be solved by a finite difference method. This is called something like Verlet algorithm, where you can see that the position of an atom at t plus delta t, I mean next step, can be obtained by a position at time t and position at time t minus delta t, I mean previous time, and the force the force or acceleration at time t, the force and acceleration related by again by Newton's equations of motion.
There is no temperature here.
No temperature, yeah, exactly. Yeah. So, you can velocity also can be obtained by t plus delta t minus or minus t delta t, and once you have a reliable interatomic potentials, you can get a meaningful results. So, this has an advantage over the experiments in terms of basically you can get an atomistic scale resolutions, the information from atomic scale, and then this also this molecular dynamics forms the basis for a multi-scale modeling in terms of MD and the dislocation dynamic simulations and then FEM to predict the better structure property correlation of a material, and this also can be used as a guide to design the experiments, and you can do the simulations at extreme environment and testing conditions unlike the experiments. And however, this has some disadvantage in terms of size and time scale limitations, and also sometimes the potential is not proper, then you will get the whatever results, it may be just an artifact, it is not actual behavior of the system. So, our motivation is basically to study the deformation and fracture in BCC system, mainly because the BCC systems exhibit different slip systems. Basically, it occurs on 3 different slip planes, you can see here. Because of that, it is the BCC, the deformation in BCC is much more complex than the FCC, where FCC we have only one slip plane and one slip direction, while whereas in BCC there are different planes and different system, they will interact, and that leads to wavy slip. So, it is a complex behavior than the FCC, and also the screw dislocations, unlike what we thought that BCC they have a 3-dimensional structure like this. Dislocations are not exactly a simple line or a simple 2D kind of sheet, but they show a core structure of dislocation is like something like a non-planar, and it is spread in 3 different planes in BCC. And also the BCC, the other interesting factor is, as you can see, that the dislocation motion exhibit a twinning anti-twinning asymmetry. What it means is, you can see that here you have a dislocations moving. Suppose imagine that you have a crystal, in that you have introduced the dislocation and allow it to move in a twinning direction, then the velocity in the twinning direction is, you can see, is very high as as compared to the anti-twinning direction. It means in the twinning and twinning just opposite to each other. So, when you move in one direction, the dislocation has a higher velocity, while in just opposite it has a much lower velocities than the twinning direction. So, because of these complexities, the BCC system poses many challenges in understanding the deformation. So, what we have done is we have taken a BCC iron single crystal systems and see how the deformation varies with respect to crystallographic orientation, size, temperature and then the grain boundaries. So, this is a model system. As you can see, in order to simulate a nanowire, we used a periodic boundary conditions along the length directions, while the other two directions were free, so that you can mimic free surfaces of the nanowires. So, this is how we have done tensile or compressive testing. This is actually a simulation box. So, one method is just change the simulation box in this manner. This is epsilon naught is a strain rate and T is a time step. So, one you can vary the simulation box in tensile or compressive manner. The other method is you make two fixed regions at the top and bottom of the simulation box and then give some certain velocity to these particles inside this region, such a way that the velocity is 0 at the top at the bottom of the simulation box, while it is maximum at the top, so that the tensile stress is applied. So, these simulations we have carried out in a LAMPS, which is an open source package, and at a strain rates of something around 10 power 8. And once you done, we have studied from different ranges up to something around 40 nanometers, from maybe 1 2 lattice parameters to 40 nanometers.
So you say that this, you don't have the thermal bath?
Thermal bath is there. No, that will be taken care by the equations of motion. We have used Neusauer thermostat to do that. Yeah. That will be coming here next. So, once you have done the simulations, you will get the system undergoes a deformation, and in order to get how the defects evolves in the systems, you have to filter the atoms according to maybe you can use energy filtering where the potential energy of the defect region is higher than the perfect region. The other parameter that we can use is the coordination number, where surfaces have a different coordination than the perfect ones, and dislocations have a different coordination than the perfect atoms, and also you can use the other parameters that is called centrosymmetry parameters, which is basically how the atoms are diverted from the center of inversion that we can get from here. So, using these parameters we have filtered the defects during the deformation. You can see we have applied the stress in all three directions. We have used different orientations of the system. We have applied tensile or compressive, for example, in this direction, all these directions. So, this is the orientation of the system basically.
Since you have a nanowire,
Yeah.
the shape itself induces some kind of asymmetry in the
Yes.
break, like which direction, like let's say that along the if you have a wire,
Okay.
but this direction is easy to break rather than this on the top.
Okay. We have applied the load along the length directions. Is it clear? Okay. Yes. Just you have a wire. Imagine a simple wire, something like this is a wire, and we applied a tensile or compression in this direction. No. Yeah. So, all the nanowires are perfect defect free without any defect inside basically, and we have chosen the orientation such a way that all the edges of the stereographic triangle, this triangle is basically that any point in this triangle represents a specific orientation of a single crystal. So, we have chosen these orientations of iron nanowires with all have a size of something around 8 nanometers here at a low temperature of 10 K. This you can see the deformation at this 001 orientation. So, basically the deformation occurs since it is a perfect nanowire, the defect has to nucleate first, right. So, the defect has nucleated from the corners of the nanowire. The front surface is removed. This visualization is shown such a way that the front surface is removed and also the perfect atoms are also removed. So, you are seeing only the defects. So, the defect first nucleates from the corner and then it grows into a, see, this is defect is like a random one, and with increasing strain you can see the defect grows into a twin, and this twin further grows into a larger twin. So, basically the deformation occurs by a simple twinning mechanism where no dislocations or full no slip is involved here. However, the twin boundaries, as you can see, the twinning is basically the movement of these two twin boundaries. The twin boundaries were assisted, the motion of the twin boundary is assisted by the motion of a partial dislocations of a of a Berger vector of this 1 by 6 1 1 1. So, once this dislocation moves here, this twin boundary will move one plane above that. So, that will be clear maybe in the next slide. You can see that. So, first the dislocation nucleates from this corner and then it subsequently moves along this twinning plane, and once it goes here, it completes one it is depicted here. Suppose you have a twin boundary here first, then this is the dislocation, this step it is moving in this direction, then with increasing strain this step will go to the surface, surface of this corner, that leads to a one step movement of a twin boundary. So, this is this step by step manner the twin grows in BCC nanovites. Tension, yeah, extension. The other then since we have seen the twinning here, then we have also seen how the deformation varies in these orientations. Basically, orientation means this loading direction here. So, we applied tensile here, then how the deformation proceeds. You can see that this is completely different from what we observed at these orientations. This orientation we have seen twinning, but here you can see that there is a complex collection, nucleation of dislocations. And with increasing strain, the whole crystal will be full of dislocations, and that leads to the moment of this dislocation, and the escape leads to the slip steps, as you can see in the surface of the nanowire. So, basically the conclusion here is the dislocation, the deformation in these nanowires occurs by the movement of dislocations. Now, by saying that, after that how the dislocations multiply, as we have told that in bulk crystals the dislocation multiply by a well known Frank-Read mechanism, but due to very small size that mechanism no longer operates at this size scale. So, what happens is, first let us see here the dislocations first nucleates from the corner, okay, then with increasing strain that grows. It is basically a mixed dislocation. It means it is a Berger vector of different the character of these dislocations at some point is edge, some point it is screw. So, with increasing strain the edge part will move faster than the screw. So, basically this time these are screw parts, this is a edge part. So, edge part will move faster than the screw. So, what leaves is only as two screw dislocations. So, basically what we can see is that one dislocation has become two dislocations. So, this is some kind of multiplication mechanisms that we can see in nanowires. And because of this you can see the large accumulation of a state, all dislocations are mostly straight in this nanowires, unlike the curved structure in bulk crystals. Then, so in other orientations also you can see that these 112 also deformed by twinning, and then 102 also deformed by twinning, but 111 again shows something like a slip mechanism similar to 001. Now, once you obtain this, how do you compare with these results with the experiments? And then we have seen that in bulk crystals what he has reported is that this is please remember this is in bulk single crystals at a strain rate of 10 power 3 and a temperature of something around liquid nitrogen. So, how does this compares with the experiments? So, in experiments what we observed is slip is observed in these orientations, the orientations falling in this region and without any twinning, means no twinning is observed here, whereas in this region he observed along with slip, he has reported twinning also. So, this is in something quite similar to our study, as you can see the twinning is reported here, but the difference between this and this is that here he observed a slip also, a dislocation movement, but here the twinning is without any dislocation movement, there is no dislocations at all. Now, previous one is basically how the orientation plays a role. Now, you can see how the loading direction plays a role. Previously was completely on tension. Now, you see that we applied compressions, the same orientation here and here. This is tensile that we have already shown that it deforms by slip, but when you change the loading direction from tension to compression, you can see that the deformation is again comes from twinning mechanism. So, this is again the twin growth and similar to what we have told in 100 nanowire. So, basically there is an asymmetry in terms of deformation. Okay. So, in tensile it is by slip, in compression it is by twinning mechanism. Now, how does this tension compression asymmetry varies with respect to the orientation? I mean, what orientation shows twinning in tension, what orientation shows twinning in compression. So, here you can see this is the tension, we have already told all these three orientation shows twinning, here the slip shows slip, but in compression the orientation these three orientations basically show slip, and in compression these two orientations show twinning mechanism. So, we have seen that this is basically, I will explain it, basically due to a dislocation character of a specific dislocation character of a BCC materials, and these simulation studies we have seen that is very good, I mean similar to what they have reported in experiments in particularly of molybdenum, which is also a BCC materials of a size of something around 15 nanometers.
Experimental systems are also single crystals.
Yes, a single crystal molybdenum nanowires basically of size of this much, but the strain rates are very lower than what we have used here. So, that tension compression asymmetry is basically because of a dislocation character. Let us assume that first I have shown it already, the 1/6 1 nucleates, and the mode of deformation is dictated by what is the next subsequent dislocations. So, if the in these partial dislocations whatever is nucleated is allowed only in one direction. You can see this is the packing of a BCC crystal in 112 directions. You can see the packing of a BCC crystal in 112 direction has a 6 layers, I mean A, B, C, D, E, F. Unlike FCC where we have a enclosed pack direction, the packing will be A, B, C, but if you look the packing of closed, I mean the stacking fault planes in BCC, that will be A, B, C, D, E, F. Now, this has a specific character, as you can see, if you move, suppose you can see here, if you move it in one direction, okay, you can get a magnitude which is equal to a dislocation, partial dislocation BCC. But if you move in opposite direction, you can see that just one atom sits just above the other, which is energetically unfavorable. So, because of this there is an asymmetry in terms of movement in this direction, movement in opposite direction. So, here this is basically what we have said twinning direction, this is what we have shown is a anti-twinning directions. So, because of this there is an asymmetry in twinning and anti-twinning direction, anti-twinning directions, there is a difference in deformation mechanisms. So, the dislocation in orientation falling in these regions moves in a twinning directions, whereas the dislocation falling in the direction moves in anti-twinning directions, and because of these there is a asymmetry in deformation mechanism. Now, how does the Stressstrain curves, a simple Stressstrain curves looks for nanowires? As we all know how the Stressstrain curve looks for a bulk, basically it increases, but for a nanowire, since it is a perfect one in the elastic regime, you can see that stress goes linearly up to a maximum something, you can these stress levels are also very high, something around 20 GPS, from 10 to 20 GPS depending on the orientation, and after that after it reaching a maximum stress, the defect starts nucleating, and once the defect nucleates there is a drastic drop in the stress values, and then it increases, I mean it is just almost constant and with some fluctuations, which is basically due to the continuous movements of dislocations and other defects. So, there is also an differences in terms of tension. Yes, exactly. Yeah. Yes. Until here it is perfect, nothing is there, but once it reaches certain value in depending on the orientations, then dislocations or twins nucleates, and that the further deformation continues by those defects. Yes. No, but I will tell you why the I will that is there. Yes, I will show you how it breaks also. So, the other interesting thing is that the twinning mechanism what we have shown is completely reversible, unlike a dislocation motion which is basically not reversible in BCC, but the twinning mechanism is reversible. As you can see, first loading is there, this is the twinned part, okay, then the complete nanowire has become twinned. At this stage if you reverse the load, it completely recovers its initial structure. So, because of this reversibility of a twinning motion, there are many reports which have shown that the shape memory and pseudo elasticity in BCC, and also you can completely see, you can completely obtain almost to a close to a zero strain even after undergoing something around 40% strain. So, this is how the size influences the deformation in BCC nanowires, particularly this is 100 orientation where twinning is predominant. You can see that up to something around 11.42 nanometer size, the nanowire shows something stress strain curve of drastic drop and then almost constant. Then again interestingly you can see it increases, almost again it undergoes a second elastic deformation followed by final failure something around here. That is mainly because you can see that in a low size, I mean this range of nanowires, the deformation is by single twin, it grows along this nanowire, the complete nanowires becomes because of this twin which has a different orientation than the parent lattice, it becomes a reoriented one, and with increasing strain it fractures in a something around a necking, but at around 132, I mean something around here 132% of strain, while if you increase the size above this range, you can see that there are multiple nucleation of twins at different places and they will interact, that leads to the twin twin interaction leads to the crack nucleation and that leads to a brittle failure. So, basically there is a ductile to brittle transition with increasing size. So, low size will deform, will show a brittle, ductile failure, where the high size range basically they show a brittle failure. Now, that is again just twinning is reversible. Yeah, basically here this, since there are interaction it is not exactly, but here since it is only one, it is reversible here completely. So, basically these all things, all these sizes are show a reversible deformation, while here because of this multiple activation it will not show a reversibility.
But you are saying that this is a typical feature of the nanowire.
Yeah.
That the dimension matters.
Yeah, size, this cross section, basically this.
When it is really very, thin or whatever. No? I can see that fluctuation
Yes.
is much less for the green.
Much less for the large size nanowires. Yeah. With increasing size, basically the fluctuations become minimal. That is again basically the defect density increases. So, you can get a more average behavior in large size because of the larger defects, you will get a more average behavior. So, less fluctuations, while whereas in small size only few 1, 2 or so.
So, this behavior is very typical of nanowire.
Yes.
The nano part of that.
Yeah, nanowires, yes.
Expected it is to also.
Yes. So, this is again how the defects. So, as I have already told that in small size there is only single activation of system, whereas in a large size there is a multiple activation which leads to the twin twin interactions and the brittle failure. Here because of single activation there is a ductile failure. Now, this is how the size influences in the other orientation where the slip was dominant. You can see that here irrespective of size all nanowires have a similar behavior of in stress strain curves. First elastic increase and then drastic drop due to defect nucleation and then fluctuations until failure. So, this is how basically since it is a dislocation dominated deformation, you observe various kinds of features like slip bands and then dislocation, slip steps here. So, all sort of things. So, basically it is no much influence of size is observed in this orientation here. Now, how the strength varies with respect to size, how the modulus varies, as you can see here that in 100 orientations where the twinning was dominant, the yield stress where the defect nucleated, the peak of the stress strain curve is decreases with increasing size, and in 110 orientation where the deformation was due to dislocation slip, the yield stress increases marginally in the beginning and then again saturates to something around some constant value around 23 GPa. Now, same behavior as you can see in the Young's modulus, and this is close to this is what we have seen in bulk single crystals of this orientations 155 GPa, 210 GPa. So, basically the Young's modulus show a tendency to approach towards its perfect one. For example, you can see the 100 it shows a tendency to approach towards this 155 GPa, whereas the 110 shows a tendency to approach towards a 210 GPa. This is a twin propagation stress. The stress needed to move to make a twin boundaries to move. So, that also decreases with increasing the size. and previously the size is varied from something around above some 10 lattice parameters. Now, if you go below 10 lattice parameters of size, okay, so what happens to the nanowire? The slip still prevails or twinning prevails. You can see this is a 100 orientation again. So, something around the size is very low, 1.61, something around 5 times the lattice parameter. This is basically. So, here only one dislocation is observed, and because of that some part of this one becomes a necked one. Basically, this is a necking part, and with increasing strain, this necking part is something does not have it loses its basis structure, and out of this non crystalline structure icosahedral structure nucleates here, and with increasing strain actually you can see this icosahedral or pentagonal structure grows along the nanowire. The iron is something around 1800. And this also shows the size dependency. If you go further low, there is not even a single dislocation slip, just like it becomes non crystalline, and then pentagonal chain nucleates and it grows with increasing strain. So, whole nanowires at some point of time the whole nanowires become a pentagonal chain, and then it breaks at very large strain, something around 265 of strain, and this we have seen that with respect to size and temperature, how I mean what sizes shows pentagonal structure. As you can see, this range has only this range has shown the pentagonal structures, while when there is a deformation by twinning, no pentagonal structures were observed. Now, this is the other orientation 111 where dislocation slip was there, and we have studied the system with respect to temperature. As you can see that from this temperature to something around 375 K, it shows a drastic drop to 0 after the peak, while at higher temperatures it shows a drastic drop, but again it does not reaches 0 here. It I mean it goes to something around 40 to 50% of strain, and so this is mainly because the nanowires here fails in a brittle manner. As you can see here, while here it fails and shows a ductile behavior to strains of as large as something around 60%. So, because of this there is some transition, as you can see at low temperatures the accumulated strains, means after this nucleation of defects, how much strain is accumulated in the nanowires is almost 0 here, while at high temperatures there is a significant accumulation of a strain. So, this is basically a transition from brittle to ductile, which is the center of, you can take the center of this as a transition temperature. This is even more clear that at up to something around 400 K crack nucleates with some minimal dislocation activity, while above this temperature there is no crack at all. The deformation is completely by dislocation movement, and that is also, so that this is the deformation. There is nothing inside the samples, only crack nucleates and grows, and at high temperatures you can see that the many dislocations activates and they moves in the crystals, and that leads to necking and then final failure by a ductile manner. So, that ductile to brittle transition is basically due to the again the interrelation between the fracture stress and the yield stress. You can see this is the the red line is what we obtained, what we got from simulation, and this is what we have calculated theoretically, the fracture stress. The blue part particularly focus it on, that you can see there is a below this temperature, this blue arrow below this temperatures, this red curve is higher than the blue curve. That means yield stress is higher than the fracture stress. So, because of this the nanowire fractures before it gets yields, whereas here the yield stress is lower than the fracture stress. So, because of this the nanowire yields before it fractures. So, because of this there is a transition in ductile to brittle. And then we have also introduced some dislocations in the nanowire, and let us see what happens, how these dislocations will influence the deformation in the nanowire. Previously it was completely defect free, right. Now we have introduced some dislocations. By these dislocations were introduced basically by twisting one part of the crystal with respect to the other. So, this is iron nanowires, let us imagine, then we divide it into two regions, then rotate this region with respect to the other one, then what results is dislocation structure or a network So, this is also called something around twist boundaries in grain boundary literature, and this also this structure also depends on the orientation of this this nanowire. If the orientation is 100, then you get a structure like this, and if the orientation is 110, you get something like an hexagonal structure. So, this we applied a tensile loading for that that kind of systems, then we can see that the network basically gets split into two dislocations, and then with increasing strain at some point of strain that a nanowire becomes again completely defective. It means all the dislocation will go to surface. So, it all again becomes a defect free. So, that is why the stress this is the first where this split into two, and then this because of the dislocation activity, then the interactions there is some fluctuations in the stress strain curve, and it is at something around 0.8 it again becomes perfect, because of which the stress goes to the maximum, and once it becomes perfect and stress is maximum, since this orientation is prone to twinning, it again shows a twinning mechanisms like a perfect nanowire. This is the other orientations where there is a hexagonal network, and with increasing strain during the elastic deformation, this hexagonal network, the dislocation core spreads into the plane of its network, because of which the stress strain behavior shows something, some kind of a non-linearity. This is not exactly linear, but it obtains some non-linearity because of this core spread, and then at this point of stress, the dislocations nucleate from the corners in interface of this network and the surfaces, and the further deformation is completely by deformations. This one network, it is what is there here in between. Rate up? Yes, that depends on angle. What we have chosen angle is basically 2 degrees. That also varies, even the structure itself varies with respect to the angle. Yes. Actually, not continuous, that is the twisting itself, that is one kind of deformation. We have first twisted and then apply a tensile load. The twisting is basically to get some kind of dislocations, that is the purpose. And then apart from that dislocation, we want to do some kind of a typical grain boundary. So, this is a twist grain, twin grain twin boundary or sigma 3 boundary, and with respect to spacing, you can see that the yield stress in tensile loading is all varies in marginal as compared to perfect one, whereas in compressive loading of this nanowires, you can see that at some point of twin boundary spacing, the yield stress is higher than the perfect nanowires. Even in terms, in presence of grain boundaries, the nanowires shows higher stress than the perfect nanowires. That is again basically because of different deformation mechanisms that we obtained in tension and compression. And in tension, it is basically what we have seen in twinning, and in compression, it is by dislocation slip. And the fracture here occurs something close to the grain boundaries. Here, since it is a compression, there is no fracture here, but dislocation proceeds by a dislocation slip. Now, how the dislocation why the yield stress shows a marginal variation here, and it shows a significant variation, that is mainly because, as you see, the deformation here is proceeds by twinning mechanisms, which is due to the moment of partials, that is 1/611 partials, whereas it is due to the slip of full dislocation like this, which has a Berger vector of 1/2111. So, because of this higher magnitude, so basically this has a higher magnitude than this one, and these twin boundaries exert some kind of repulsive force on the dislocation motion, and when the Berger vector is higher, it has a higher, it leads to the higher repulsive force. When the Berger vector is lower, it leads to smaller repulsive force. Because of this weak or smaller repulsive force, there is a negligible variation whatever may be the twin boundary spacing. While in this case, since it is a significant repulsive force, and it shows a strong dependency on the twin boundary spacing. So, how these two twin boundaries have spaced with respect to each other. So, this is how dislocations or twin transmits transmits through the grain boundary. As you can see that basically the twin is here, how it grows to the next grain. This is one twin boundary, and this is twinning mechanism that is coming from the deformation. So, how it goes to the next grain. As you can see that it comes and interacts at here at this point, and it leads to the parcels which are transmitting along the grain boundaries. It just does not go to the next grain, but the dislocations moves along this twin boundary plane. Okay. And also there is an accumulation of dislocations, basically the parcels at at the downside of this twin boundary, as you can see here, and at larger strains, then that dislocations also transmits to the next grain. So, basically it depends on what is the strain, whether it transmits to the next grain or not, depends on the transmission strain, and this is where you can see the twin boundary acts as a nucleation sites for a dislocation. So, this is something like curved twin boundary in BCC, and with increasing strain these parcels will come. This is one parcel, you can see here, it came and it's accumulated here, and the next parcel comes, that also comes here, accumulates here, and then again third parcel will come and accumulates. Now, once the 3 parcel comes, that leads to the formation of a full dislocations, which dissociates from the twin curved twin, and so because of that the initial twin boundary becomes smaller in size. So, you can see the reaction how it is goes. So, this 3 parcels basically leads to 1 4 parcels. So, this is the direct transmission of single dislocation. As you can see, there is a dislocation, previously it is basically twinning, now it is a full slip. So, there is a twin boundary here, and the dislocation is coming from this side, and it directly transmits the next grain. While in some cases what we observed is that it goes into a symmetric direction. That means, you can see the first directly the red line, you can see the dislocation comes here and then goes to the next plane, while in other cases the dislocation maybe comes here and then goes to in a symmetrical plane. So, two possibilities are there. The dislocation either directly goes to the same plane, or it can also transmits in a symmetric plane. That is again basically this is not this two reactions are not possible in FCC systems. In FCC basically what we observed is symmetric transmission, but in BCC it is direct transmission is also possible. That is basically the structure of systems, slip planes is favorable for direct transmission as well as the symmetric transmission. This is some work on copper. Again we have seen the different we have taken different orientation, how that deforms, and what we observed is in tension all orientations show twinning, while in compression some parts of this orientation show twinning, while others show dislocation slip, something like this. And this is again basically because the Smith factors means which tells us that how much the stress is resolved in that particular plane. So, because of that this orientation shows twinning, while this orientation shows slip, but in tension actually the theoretical prediction what we can get from Smith factor is that you should observe slip, but in tension what we observed is all orientation have shown twinning. That is maybe basically some surface stresses which are not taken into calculations here. So, because of that there is some difference in this region. So, again how the loading changes here, something similar here, you can see that it is basically by a partial dislocation in tensile, and it is because of the full dislocations. So, that is full or extended dislocations in compression, and so when the nanowire undergoes a twinning mechanisms, when the twin interaction leads to the formation of something like a 5-fold twin boundary, which is of interest, and then how the twin interaction leads to the formation of a higher order grain boundaries. So, basically we have initially you have 2 twin boundaries, this is let us say here and here, and the interaction of those 2 twins leads to the formation of a grain boundary, which is something of a sigma 9 character. Okay. Then how the dislocation density varies in the nanowires with respect to different sizes and all. As you can see that this is in copper. So, initially the dislocation density is maximum at yielding, where the stress is also higher, and then with increasing strain the dislocation density continuously decreases. It decreases, the decrease is rapid up to some point, after that which it is almost constant. So, this decreasing stage we call it as a dislocation exhaustion region, where the nucleation is lower than the exhaustion, means the exhaustion rate is much larger than the nucleation rate. Here since almost the nucleation and exhaustion both are equal, so because of which you observe you see the constant in dislocation density, that we call as a dislocation starvation region in the nanowire. and this exhaustion rates of a dislocations in the nanowire increases with the decreasing size, as you can see here, and also how the average length of dislocations within the nanowire changes. You can see that it is almost constant in all the nanowires except the smallest one, because it cannot accommodate, the wire size itself is 1.44. So, it cannot accommodate a dislocation of size more than 1.446. So, that is the limit, but for something 43 also, means a nanowire of something around 43 nanometer also the length of dislocation is close to 2 nanometers. So, and in dislocation exhaustion region they show almost a constant, while in starvation region they show large fluctuations. These large fluctuations are again because of the continuous nucleation and then exhaustion, nucleation and exhaustion. So, each nucleation and exhaustion region leads to this kind of peaks and then drops. So, this is again I mean how in very smallest size nanowire, something around here, you can see that one dislocation comes and it is some cascading kind of behavior. It reaches the opposite surface, again from the same site nucleation, I mean one more dislocation nucleates and it reaches this surface, and again it goes to other surface. So, this cascading behavior of dislocation is also seen in the lowest size nanowires, and this is how the yield strength varies with respect to cross section size, and this is how the failure strain varies with respect to the nanowire size again. And in copper also we have seen how the twin boundaries influences the deformation. You can see this is the vertical twin boundaries, and if you apply a load here, you can see that the various dislocations nucleate and they interact, that leads to something around a stair rod formation at the grain boundary, and with further deformation the stair rod again dissociates into two trailing kind of partials, and that leads to a formation of a full slip from two partial slips. So, this is again we have seen how the stacking fault. So, basically in FCC the single dislocations dissociates into two partials, right, and this is we call it as extended configuration, which is separated by, which is of a width which depends on many factors, and with respect to the thickness of this film, what we observed is that the thickness of this dislocation also, width of this dislocation also changes, and that is basically increases with increasing the film thickness, and that approaches to something around a bulk value where there are no surfaces at all. So, that is our work. Any questions?
So, in this last slide,
Yeah.
you were talking about stacking fault. So, why do you say the single dislocation? Is it a single dislocation?
Yes, yes.
And then what do you see?
This is a single dislocation in FCC system. Then that single dislocation actually is not stable in FCC system. It dissociates into two partials, right, separated by some stacking fault that we can see here. Now, the distance between these two partials depends on many factors. Now, in this, because the size, the system size is very small, where surfaces also plays a role. Okay. So, the thickness of this, which comes from which is if you vary the thickness, surface contribution also varies. So, because of which the width also changes. So, basically these surfaces have an influence on the width of this dislocation.
But no more further dislocations will be generated. It will always have two clockwise and anti-clockwise dislocations.
Yes, yes. No, actually this is we have introduced and then equilibrated, nothing we have done. We have not applied any stress or strain, it is just equilibrated.
Yeah, I understand.
Yeah.
I missed the part, but what kind of potentials are you use, especially for the BCC?
BCC actually we used EAM, that embedded atom method, EAM potentials. EAM.
And is this stable? What do you do in the borders? In the borders, the atoms can live in the open boundaries. If the atoms wants, it can
No,
live.
they cannot live.
So you put some.
Rigid, it is not exactly rigid, but it is a free boundary, but atoms cannot leave the system.
How do you ensure that? How do you ensure that
You reflect at the boundary, you reflect the atoms at the boundary, something like a reflection.
But this could be that this is stabilizing the structure.
This could be,
The structure is not stabilized by this condition. So without this condition, the atoms will leave.
system will lose some atoms, then that leads to the problems.
For example, like effects like buckling, etc. This is ruled out, right, from this kind of.
No, you can do it.
You can have buckling also.
Yes, yes, yes. That's what compression is basically. If you make it,
Not that you need the dislocations to be aggregated at that.
No, but then, so if, no, the thing that I think, so if, how are you treating the surface? So is it a free surface?
free surface, but the atoms can at the surface cannot leave the box.
And the box. They cannot leave the box.
Yes.
But they can leave the surface.
They can leave the surface. Yeah, they can leave the surface, but they cannot leave the box.
So it's like
Yeah, exactly.
I have another question. So your initial configuration is always a perfect crystal. Yeah. Is this realistic?
Which one? Not getting.
Your initial configuration is always a perfect crystal.
Yes, yes.
Is this realistic? So, I mean, reality, everything is
In reality is not possible, but if you see the nanowires of that size, the defect density is extremely low. So you can approximate it as a perfect one. That was the.
Temperatures that you are working at, so I presume you are equilibrating at these temperatures.
Yeah, of course. Yes, yes.
And also, I mean, you don't see defects coming in at
No. Even at 900K, nothing has come because size is small, which makes it.
No, and related question is, I mean, are polycrystals interesting in this case? And if you started off with a polycrystal?
Yeah, we have actually started. We've done some work on polycrystal, and we have created a structure of, because a polycrystal, the problem is creating the structure itself, which what kind of polycrystals we create. So how do you get the data from the experiments? What kind of grain structure they have it?
So in experiments, how would they prepare the nanowires? What is the, so during the preparation itself in the experiments, can't they have polycrystalline structures?
Actually, there are very rare where nanowires have a polycrystalline structure, but some people have characterized it.